From 2006 to 2012, I was project officer at YABA, the Swiss Federal Institute of Aquatic Science and Technology. Right now, since 2012, I work at the Senegal National Sanitation Utility, leading the gate-funded project on fecal sludge management separation. This session of this afternoon focus on fecal sludge treatment using physical, chemical methods, using drying bed and also using wetlands. This topic is very important because we realize that in developing countries, we propose a lot of technology, but the conventional techniques previously implemented in developing countries no longer works. In terms of performance, accurate performance, in terms of footprint, in terms of reuse, we realize that we have some. And the presentation is therefore maybe will answer or will offer some answers of this critical question. Each presenter will present in 15 minutes because we have the chance, we have just for free presentation. We have planned to present during 15 minutes. And after each presentation, we will give the floor to the participants in order to ask 2 to 3 clarifying questions. And when we finish all the presentation, we will organize a sort of panel. We will have all the presentation in front of the participants, and we will discuss in depth about the presentation. I will be very happy to welcome Dr. Atitaya, the former teammate from YAPAC. Dr. Atitaya is a senior research specialist at the Asian Institute of Technology, and he specializes on decentralized wastewater treatment systems and fecal sludge. What Atitaya is presenting today, a study focus on the effect of different filter media on nitrogen transformation in the wet control concept of wetlands.
Okay, thank you very much, Bai. Okay, welcome to my presentation in the topic of nitrogen transformation in each media layer of vertical flow conducted with land treated fecal sludge. For this slide, I just would like to share with you about the situation of fecal sludge management in Thailand. But then on our field survey, we found that the capacity of treatments in Thailand only 40% that can receive of the fecal sludge generated in our country. But however, 90% of that 40% still improper operate or even cannot operate well. Then it means that like 98% of fecal sludge in our country also go to the effluent area and also go to the receiving water. Then, as a researcher, we also try to manage with the sludge. And this is just the ideal of the researcher that try to close the loop. Like we try to treat and also we try to reuse. And for my presents, I just focusing on the last part of the chain, which is treatment and reuse. Then on our experience, like 15 years as AAT, we already confirmed that vertical flow constructed wetland had the high efficiency of promising treatment efficiency for fecal sludge treatment. And for my presentation, if we know about the nitrogen transformation of the system inside the system, it will be good and also it can help for the design of the system. Whether you would like to increase the treatment efficiency or if you would like to reuse the nitrogen, we also can model if we know well within the system. Then for my study, we already know that nitrogen nitrification and also denitrification occur in the system of each layer, such as in sand layer or gravel layer. But for this study, we would like to go in depth to identify the DO concentration or oxygen fluctuation according to the time of the operation inside the system again. And this one show you the experimental setup that we have at AIT. We use the plastic tanks, 1 meter by 1 meter and about 60 centimeter of the media. And inside the system, we also put the probe here in order to measure DO concentration, pH, and ORP to know the fluctuations of the DO inside, like a real-time monitoring after we feed. And also from the east layer, we also measure the percolate that just pass through sand, small gravel, and also large gravel in the bottom part to see the fluctuation of each parameter. Okay, sorry about that. Okay, this one show you just the sampling points and also the point that we put the probe for measure BOD, ORP and also pH inside the system. And for the operating conditions that we also use the 250 kilogram TS per square meter per year once we feeding to the system. And after feeding, we take the sample every hour, just 1.5 days, to see nitrogen transformation in the system. And after that, we measure every day until at least the 6th day of the operation. And we also measure the parameter as occur in this one, in order to calculate the nitrogen transformation inside the system. Then this one just show you the nitrogen transformation. For here, TN from the Faecal sludge. After feed into the system, this is the represent the accumulated sludge on the top part. We found that about 50% of organic nitrogen accumulate on the surface of the system, and also just some parts of ammonia can volatilize into the air. And then for the remaining of each form, we flow down to the sand layer, which is show you here. And organic nitrogen change to ammonia by ammonification, which is about 4%. And after that, ammonia also can change to nitrite and nitrate, about 3%. And then the remaining also can fall down to the bottom part, which is gravel layer. And also more or less the same ammonification, nitrification, and also denitrification still can occur at the bottom parts, but maybe at a different percentage. Then for the remaining of all the nitrogen form will fall out with the percolate. By the overall process will be take about 6 days because we feed once week feeding. And then for this one, we would like to confirm nitrification and also denitrification that can occur in the system by we measure also DO concentration in each layer. And this one is just a general unit model that can occur in each layer. We had from my study, we also can confirm that every reaction can occur in every layer. Next, we would like to focusing on nitrification and denitrification here. And then this slide show you the DO concentration that occur in each layer. We can see that with the percolate of Faecal sludge, it contains DO about 4.5 milligram per liter. And then after feeding into the system, this one represents the concentration in black sand layer, which is on the top part of the system. It shows that about after 6 hours of the operation, from 3.4 go to 1.9 milligram per liter. And after that, after 24 hours or 1 day, the concentration of the DO leads to 0, which is represents an aerobic condition. And then from the middle layer of the media, which is small gravel and also large gravel, which is present here. Before feed with the fecal sludge or at the starting stage, as gravels still have slightly aerobic condition, which is about 1 milligram per liter of DO still appear in the system. And then after 6 hours, seems like the percolate of sand layer fall down to the middle part, which is the DO concentration can go up a bit to 1.7 milligram per liter. And then after 1 day, DO also drop down to nearly 0 or anaerobic conditions. And at the bottom part, which is large gravel, before feed, also just have slightly DO concentration or anaerobic condition, just 0.3 milligram per liter of DO. And then after 6 hours of feeding, seems like percolates from the top part from increase also bottom part. Then DO concentration can go up a bit to just 1 milligram per liter. And then after 1 day also can reach the anaerobic condition. And then this is also just show you the transformation in sand layer. Sorry, maybe this one is quite long with the typing, but about 60% of organic can remove in the top part and also sand layer, and also just 3% of ammonia can remove on this part. And the other things, the nitrites and nitrate also increasing in the sand layer. And then if we comparing the occurring of the nitrites and nitrates in sand layer together with the DO concentration, we found that it's still not quite balanced, because actually from my hypothesis at the first time, I thought like if we know DO concentration, then it may balance with the occurring of nitrites and nitrates in the system. But after we measure, we found that the occurring of nitrites and nitrates in the system still higher than the concentration that we can measure in the system about 2 to 3 times. Then it means that oxygen in the system may come from the other source, like from the plant root, and also can come from the air. This one maybe can be the further study. And then for small gravel layer also more or less the same, but not much reaction as sand layer. Then just 7% of organic removed in this level, and also 10% of ammonia also removed in. And the occurring of nitrite and nitrate also removed here under denitrification reaction. Also for the bottom part gravel layer, the remaining of every form also removed here. Then I would like to come to the conclusion. For the upper part, ammonia can transform by nitrification under aerobic condition, which is we can confirm the DO concentration in the system. Because based on my previous study at that time, I not measure DO concentration yet, but for my study I also got question a lot, how can nitrification occur in the media or inside the sand media. Then I also measure DO concentration to confirm the reaction rate. And also within sand layer itself, denitrification also can occur, because we also can confirm by the anaerobic conditions. And then at the bottom part, both net reaction also can occur at the bottom part, nitrification and denitrification, because the oxygen also can come with the percolate that fall down from the fecal sludge and also from the sand filter layer, and then go down to the bottom part, and then the remaining of the oxygen can slightly occur nitrification and continue with denitrification according to the Okay, that's all for my presentation. But it's like is that the recommendation, as I suggest, right now we already know the DO concentration of oxygen within the population, and also we know the building removal, which is how much oxygen used, and also nitrification. But still, we still cannot quantify with the oxygen transformation from the air into the system, and also dissolved oxygen in the biofilm surrounding in the cell, and so last one also oxygen transformation from the tank root. This is made the further study of this research. Okay, thank you very much.
Thank you, Dr. Faecal, for the nice presentation. We take 3 questions just for clarification.
Have you studied the effect of depth of different media on the transformation efficiency? Like, can you increase the transformation by increasing the depth of gravel layer or sand layer?
Yes, for each layer, for sand layer, we have about 15 centimeter, and then for small and large gravel is about 20 and 20 centimeter.
What happens if you increase the depth? Does it increase the
Yeah.
Because all the transformations have been expressed as meter square, area of the bed, not the depth. So I was wondering what is the effect of depth? What could be the effect of depth on the removal?
Yes, actually, in our previous study, I also have a study try to increase the depth of sand layer, and for that one, it also can increase the efficiency of nitrification reaction of the system also, but it may reduce denitrification, which is you may have a lot of nitrite and nitrate, which is not nitrogen also cannot remove within the system, but depend on your purpose. If you would like to reuse of nitrogen, it's also quite good. If you would like, if you can increase the depth of the, sand layer in the system.
Is there a question?
Okay, thank you for the presentation. I have some query, just like what is the temperature at the time of my study, as well as what is the organic carbon content in the raw on that wastewater, organic carbon as well as the inorganic carbon, and pH also. Can you?
Organic carbon, we also measure like in terms of COD and DOD, right?
Em bấm đây từ đầu đến cuối.
Nhưng
sau file nó chỉ có được 11 phút là hết file. Tôi làm cái đáp
because COD is about 3,000 milligram per day, and also for the DOD is like about 900 to 900 milligram per day. That is the average concentration of the characteristic of fecal sludge in the system. But for the calculations in the system, sorry, now I cannot measure that because in each layer I just try to focusing on the detail of nitrogen transformation.
Regarding this, I think the nitrogen monostructure will be, and what is the limiting factor of this study? Because the limiting ratio, among the people that nitrogen, there is the limiting factor, limiting state also. Instead nitrobacter to nitrosomonas factor, that's the prototype. What may happen in this? Because pH is also not mentioned here, and so that is prototype.
Yes, thank you. For PS, actually, sorry, I'm not sure here, but I also measured the PS is like about 7.228 along the operation time. Once we feeding and we keep the chocolate inside the system about 6 days, and the PS always fluctuates about 7 to 8.
Okay, the last question. Okay. from West Netherlands. And he is an experienced engineer in provision of water and sanitation services, especially in rural areas of developing countries. On this lecture presented today, the Sludge tunnel is presented with special focus on practical design, operational parameters such as sludge loading rate, plant species, what is the harvesting period, land requirement, what are the main bed configuration proposed, and what are the staff configuration. You have 15 minutes.
Good afternoon, ladies and gentlemen. I'm honored to stay here and to share a little bit about my experience doing some research in India. I did this research in Gujarat. I will explain this system, which is called toilet-linked biogas plant, which was is implemented successfully in India. Let me introduce this topic to you. Well, this morning was mentioned a lot of, we heard a lot of data about the situation of sanitation in India. And just to remark it, we know that 2.5 million lack of appropriate sanitation in the world. And we also have to consider that India, after China, is the second largest population in the world. One person every 6 is from India, you know that. The situation about drinking water has been improved a lot in India, but the situation about the sanitation is one of the main issues that the Indian government and the different institutions are trying to work on it. The most interesting data was mentioned also this morning, half of the population practice open defecation. It was the main purpose to start doing this research in India. This is the system called the Devandu plant. It's developed by India a lot of time ago. Mainly the main purpose of this system is to produce biogas using cow dung. It's used in rural area more than 20 years ago, and it's working very well. It produces enough biogas for cooking, for a meal every day. But since the government and other institutions are implementing a lot of toilets, the next problem is what are we going to do with the fecal sludge? In this specific case, what we did, we linked the toilet to this existing system. That's why it's called toilet-linked biogas plant. This system is quite good because it produces enough energy for cooking, and it's quite simple. And also the effluent of this system is very well appreciated because in rural India, most of the people, the main activity is agriculture, and they reuse the called slurry in agriculture. But once they linked the toilet, the problem was that the effluent, the slurry, has high concentration of pathogens. That's the main problem. It's a picture of how it looks in the field, the system. You can see this, the inlet to feed, the digester is underground, and here's the effluent, here's the toilet. The main advantages of this system, it has a low land requirement, it could be underground, it produces methane, produces biogas, and it could be applied in small and large scale, but the main disadvantage is the removal of pathogens, and also low removal of nutrients. Also, it was very little known about the characteristics of this product. That's why we did this research to determine the characteristics of this effluent, and also we proposed the implement of sludge treatment wetlands to check if it's a good system, if we can remove pathogens, and what are the characteristics of the byproducts after this system. We characterized the slurry, and we implemented 8 pilot-scale experimental units. About the setup of the experimental unit, we selected 2 different species of plants. The first one is called Scarca, it's a local species of Phragmites. And the second one is called Napier Bajra hybrid grass. It was developed by the local university in India. The main use of these plants, the second, is for feeding the animals, cows. This is how it looks, the experimental unit. As it was mentioned in previous experiments, we also included the aeration pipes because in the literature it's mentioned it improves the performance. Also, we used 4 different layers of sand and gravel, and we used 6 plants per square meter, the density of plants. The operation, we had to dilute because the concentration of total solids was very high of this product. It was built 8 experimental units, and the feeding and resting period was 1 week. About the sampling, we sampled 2 different products in the treatment wetland. At the top layer, we have the dried sludge. Here it's how it looks at the time of sampling. And at the bottom, we sampled the water leachate. As you can see, even looking just the difference in colors, we applied 4 different loading rates, 40, 80, 120, and 160 kilograms of TS per square meter per year. And this is the influent, and this is at different loading rates, the quality of the samples of each experimental unit. About the results, the characteristics of the sludge, that was the average of temperature, 23, almost 24 degrees, and the TSS was almost 12%, pH range between 6.8 to 7.3. The nutrients, it is good to mention the concentration of nutrients is quite high. That's why this product is applied successfully in the agriculture. The local farmers know that this product is very good. And the organic matter, we measure the volatile solids. It's a little bit high. And the pathogen concentrations also, we measured Salmonella and E. coli. Salmonella was absent, and the E. coli is a little bit high. About the dried sludge, what are the characteristics of the dried sludge? We checked the sludge dryness. As you can see, we have the results for 4 different loading rates. And there is a tendency of a linear increase, but there is a recommendation for reusing the final product, the dried sludge. It should be around 35% of moisture content. This is an indicator to say, okay, this is the recommended factor. We can assume that at least 100 kilograms of TS per square meter per year is the recommended loading rate. And also we checked the stabilization. You can see the influent, it was around almost 70%. It was reduced at different loading rates. At low loading rate, of course, there are more reduction, more stabilization of the product. About the nutrients, this is the quality, the amount of different components of nitrogen, and this is at different loading rates what we found in the experimental units. These values are similar to other materials like compost published in papers, in scientific papers. About the E. coli, this morning was mentioned that it's not a very effective method for E. coli reduction. That's true. We have the two classifications for reuse. The class A, which means if we are below the class A, we can reuse the product without any measure of any health problem. But also, if we are below class B, we can reuse the product. We reach these values, but taking some measurements in order to handle with using the safe tools and materials. About the water that was collected in the bottom, it's very important to measure the quantity of water. Why? Because there is this factor, the evapotranspiration. That's why the dry bed or sludge treatment wetland can change. It's not the same design for everywhere. It depends a lot of the local conditions. In this case, for example, the evapotranspiration is almost 12 millimeters per day. And if we work with very low loading rates, we will see that the plants will start dying because they don't have enough water to grow and to develop all the activities. But this is also, we need at least 110 kilograms TSS for square meter per year to have enough water for the plants to do their job. About the quality, these are 4 different loading rates, the parameters, and these are the guidelines recommended for US EPA. And you can see most of the parameters are below, under the regulation. That means the water can be reused, at least in this case, the water that we collected can be reused for irrigation. One interesting parameter here is the sodium absorption rate, which is here. This is, in almost all the cases, we found the below of the recommendations or in the guidelines. Well, just to conclude, what we have this toilet-linked biogas plant. It's a successful system implemented in India. It's fitted with the cow dung and the toilet daily, and it generates enough biogas for cooking every day. Also generates slurry, which is a very well appreciated product for reuse in agriculture. We found that applying this technology, sludge treated wetland or planted dry beds, it's just a question of nomenclature, I think. We have 2 products: the dried sludge accumulated in the top layer, and the leachate, which is collected in the bottom. Both of these products can be applied in agriculture. They do that. And also, additionally, the plants, because we tested different plants and we can test, I think, a lot of varieties of plants. In this case, one of the species was specially developed for feeding cows. Also, it's possible to reuse it. Somehow, we can close the cycle applying this technology. Well, I want to acknowledge the different institutions which were involved in this research: UNESCO ING, Universidad del Valle from Cali, Colombia, Bill and Melinda Gates, Finish, the local Indian organization, and Waste, the Netherlands organization based in Netherlands. Thank you very much. This is a picture how the system, how it looks. After we finished, we also were able to transmit to people how it's important, and they started applying. You can see after the system, it's not like very well designed or very well structured, but it was applied, and they are using the system. Thank you very much.
Thank you, Mr. Madina, for sharing the system. So the reason why you're doing this is to reduce the salmonella concentration, is that right?
Not salmonella concentration, because we didn't find salmonella. E. coli. We use the E. coli as an indicator of pathogens.
But the E. coli was still in the meat, right? So you didn't reduce it?
Yeah, we reduced, but let's say we were looking to reduce, to classify as like class A, which is a product you can handle without any safe measurements, health problems, but we couldn't reach that, that class A. But class B is also possible to reach, but you have to take care about how to handle the product. We reached that, that's the results.
You were already in class B when you started.
Yep.
Okay.
Hi, thanks, Grover. Two questions. First of all, why did you choose that configuration of gravel? And did you try with different configurations during your experiment? And secondly, can you comment upon the quantity of biogas that was produced and, for example, how much cooking time it gave the users? Thank you.
Okay. About the configuration, I'll try to find the slide. But it's a general recommendation of designing these systems. I added one extra layer. Usually we just use 3 layers. In most of the experimental units, we just usually recommended 3 layers for gravel, fine gravel, and sand between 10 to 15 centimeters. That's the most used range. Why we applied 4 layers? First of all, there was the material was available. Well, that was one of the reasons. And the second, it was to test, well, at least to compare with the existing design if it has a difference. But it was not the focus of the research, but it was additional, let's say, additional finding that there is not that much difference. And regarding to the biogas production, we didn't measure because it was not part of the research. But what we are doing, we are having right now another research project in India, in the same place, to compare an aerobic digestion system without toilet and with toilet. And we don't have the final report, but I can comment that there is more methane production using the toilet liquid biogas plant. This is a project which is still going on. We don't have the final results. Once we have, hopefully we can share it. But regarding to this system, how much energy, we didn't measure the production of biogas, but what we measure is, for example, how, if it's enough energy for cooking, they have, because they maintain very well the system, because they need the energy for cooking, and they have enough energy for cooking a meal every day for a family for 4 to 5 people. That was the range.
You can take advantage of this small number of the take 2 more pressure. On the other side.
Thank you for your nice presentation. My question is, usually wetlands subsurface like this vertical or horizontal, they are clogged. Do you know about how long this will run?
About clogging?
Clogging.
Yep. Well, it's also not part of the research, but what I can share about clogging, for example, in Europe, they use this technology for very long periods. One interesting parameter of this is the accumulation rate of dried sludge in the top layer, more or less, is like 10 centimeters, 10 to 15 centimeters per year. Then that's why this system is very, very, very applicable. And there are a lot of natural processes, let's say, like the plants which are growing, they are moving, they crack the sludge. There are oxygen transfer from the leaves to the roots. There are a lot of natural processes that happen in this system which helps to treat the product. And there are cases in European countries where they empty every 10 years, for example. They accumulate like one meter of dried sludge in the top layer. But it's very interesting. But for this small case, let's say at household level scale. What they need, because they are harvesting 2 times per year or 3 times per year, they don't need the fecal sludge or the treated product every day. Then we can design a wetland which you accumulate. Let's say your emptying period could be 6 months, could be 4 months or 1 year. And another important parameter that we check, the plants grow almost to 1 meter in 1 month. And they can harvest every month the plants, they can feed with this. And we can play a lot with this with the parameters. But that's a very good advantage of this technology.
There is no growth.
Well, it was not, there is no information about clogging.
It is something you put. Yeah. Yes. Last question.
Okay, thank you for the excellent presentation. I would like to know about what is the shade ratio in influent, and the second one is what is the proportion of mixing? Can you clarify that?
Mixing what?
Mixing that toilet Faecal and or biogas. What is the problem?
Why do we leak? You're asking why?
Yeah.
I tried to explain at the beginning. Because the system, the anaerobic digestion system without toilet is already 20 years old and it's still working in this area. And recently, because all these areas, they practice open defecation, they don't have toilet, and the government and different institutions are building toilets. What's the next problem? How do we manage the fecal sludge collected in the toilets? That's why one solution could be linking to this existing system, and we evaluated that.
Okay, so I asked, what is the CM ratio in the reactor or the biogas? What is the CM ratio? Carbon to nitrogen ratio? Because that would be a good question.
What I propose, you can put this answer as a panel.
Okay.
Otherwise, we can use SuSanA. Thank you very much. Maurice Gold is a project officer at Sunday, the Department of Water and Sanitation at the Stream Institute of Science and Technology. His applied research focuses on innovative solutions for treatment and issues of fecal sludge. The study presented today focuses on the use of Senegal locally produced conditions such as ketosal to increase dewatering of fecal sludge, thereby reducing treatment food waste or increasing treatment capacity of existing fecal sludge.
Thank you, goodbye, for the kind introduction. Thanks everyone for coming to my presentation. I'm presenting the research results from Dakar in Senegal, which is part of a research collaboration between Sunday and the University of Sheikh Anta Diop in Dakar, Mr. Seydou Niang, who is also here. I thought when I made a presentation I have to build a strong case about why we're looking into fecal sludge treatment, but I think it's clear from what we heard yesterday and today. Still, low-income areas are among the fastest urbanizing regions in the world, which is going to increase quantities of fecal sludge to be treated in the future. But even today, as we can see at these 2 examples here, Dakar in Senegal and also Kampala in Uganda, there's already, even if treatment system existing, there's a need to extend these treatment capacities to meet the needs of the people. So in Dakar, there's 3 treatment plants existing, as shown here on the map, with a treatment capacity of around 1,500 cubic a day, but much more remains untreated. In Kampala, there was a treatment plant which started operating early mid of last year, and it was shortly after it started operating, it was overloaded and there's a much larger need to extend these treatment capacities. Both treatment plants rely on sand drying beds to treat the fecal sludge. As you know, fecal sludge is mostly water, so one of the main steps when treating fecal sludge is separating liquids and solids. Drying beds are commonly used all over the world. They have advantages of low operational costs, low capital costs. They benefit from the semi-arid climate in sub-Saharan Africa, but a big disadvantage is they need large drying spaces. So what we are looking at is ways how we can increase the drying footprint. And as you can already see on the top right picture in Kampala, treatment plants are now tended to get located outside of the city, which is a good idea in a way, but when you're considering that we're mostly transporting water around the city, it then increases fecal sludge collection transport costs, which then at the end get passed on to the household level. So what we're looking at is something which, if there are wastewater engineers around here, I'm kind of a wastewater engineer trained in Germany. Polyelectrolytes and organic polymers, metal salts are used in wastewater treatment to increase dewatering properties of sludge. So sludge particles are usually negatively charged, and by adding these materials, mixing them with the sludge, these negative charge get overcome, and bigger flock particles build up, which are easier to dewater. So that's what you see here on the right, this column, which is untreated, unconditioned fecal sludge, and then when you treat it, when you condition it with, for example, these polyelectrolytes or metal salts, they build in larger flocks, which affect settling and also dewatering. And I'm going to today focus on dewatering, how conditioning can reduce treatment footprints by increasing the dewatering properties of sludge. These conditions are nice, but experience show that using imported expensive consumables for fecal sludge treatment are one reason why fecal sludge treatment plants in sub-Saharan Africa, also in other countries, are not sustainably working. There's a paper I recommend from my colleague Magali Bassin on success and failure assessment on fecal sludge treatment technologies. We should learn more about why treatment technologies are working and why they're not working. So as part of this study, we were looking in using commercial conditioners, so conditioners which are available in Europe, the United States. I believe also in Asia, conditioners are produced, and we were comparing them with conditioners which are locally available in Dakar and potentially also locally available in other low-income countries or other areas of the world. I think we shouldn't not always talk only about low-income areas. There can also have implications for other regions. So these are the ones we're looking at: Chitosan, Moringa oleifera, Jatropha crocus, Calotropis drosera, and lime. I think I don't have to say much about lime. Chitosan is produced from chitin, which is a part of everyone's hair and nails, and is commonly produced from shell of shrimps. So all areas around the world, big cities, which are located next to the sea, have the potential that there's production of this fish waste, which can be produced with the chitosan. Moringa oleifera is at the moment a bit of a hyped plant. In Europe, you get it now as a tea. It's also produced as an oil. In Senegal, it's also a popular food. And the leaves of the Moringa oleifera seeds are eaten. So these were the local conditioners we were looking at. To assess if these conditioners can really improve dewatering properties, we're conducting lab and bench scale experiments. And in the laboratory, we're looking at specific filtration, which is measuring kind of the resistance. How difficult is it to dewater, to get water out of the sludge, which is done by adding conditioned sludge into this funnel and then sucked through the filter. So we're comparing unconditioned sludge, conditioned sludge, and also different dosages. And as you know, drying beds are not driven by a vacuum pump, they're driven by gravity. So obviously these lab scale results only have limited application for full scale treatment. Therefore, we're comparing our lab scale results with bench scale experiments, constructing these dewatering columns which are shown on the right. So I want to now dive into the results. These are the results of the lab scale experiments. First of all, the first two columns compare dewatering of unconditioned fecal sludge with wastewater and drinking water sludge from the literature. So the higher the specific filtration, the lower is the dewatering property. And as you can already see, it's very difficult, or it's more difficult to dewater fecal sludge in comparison to wastewater sludge. Column number 3 to 7 shows the different conditioners. So we're now looking at number 1, unconditioned fecal sludge, and 3 to 7. And we see that except for Jatropha seeds and Calotropis leaves, conditioning increased the dewatering properties. This seems to be clear for Moringa rufella, column number 3, for lime, and for commercial conditioners, and this variability is a bit higher for chitosan, but remember we did it at different dosages, so the higher end of chitosan means there are lower dosages, whereas the lower end means still a higher dosage. When we were looking at comparing these results to our batch scale experiments, we saw that results were in general 4 to 30% lower, which has different reasons. One is, for example, that we didn't use a vacuum. Other ones is that lab scale experiments obviously controlled conditions, they should always be treated with care. This here shows a dewatering curve. So how long did it take to dewater the percolated free water? The black filled circles show unconditioned sludge, and as you can see, the dewatering was faster when the sludge was conditioned with, in this case, lime and chitosan, compared also to these commercial conditions. And as you can also see is that lime and chitosan compare well with commercial conditioners. So saying that you could use commercial conditioners, they're also effective in increasing dewatering properties. So now you will ask me, so what does it really bring? I'm operating a treatment plant or designing a system. And here you can see how much percentage faster was percolation of unconditioned sludge compared to conditioned sludge. And as you can see, it was between 60%, it went from chitosan to up to 99% for commercial conditioner, which is C to 2064. And this is then the time you can subtract, or which you can reduce your treatment time and reduce your treatment capacity, and increase your treatment capacity or reduce the footprint of newly constructed beds. In Dhaka, depending on the loading rate, the time it takes to dewater sludge on drying beds is usually between 2 to 9 days. So this time you can cut by 60 or more percent. But I think also this also has implications for other, not only drying beds, also for mechanical dewatering or for container-based solutions. So we're not only looking into drying beds. Now we didn't find the solution for fecal sludge treatment in this study. All the conditioners have advantages and disadvantages. I had big discussions with them before I started the study, because he was saying you don't even have to look at Moringa oleifera because it's not going to be available, these seeds. And he was right. So listen to your supervisor sometimes also. So as you can see on the top one is the different dosages required for conditioning, so around 4 kilograms per ton total solids for chitosan, and 625 for Moringa oleifera. And these quantities for at least a centralized fecal sludge treatment in urban areas, so talking from, like, let's say above 300-400 cubics a day, this is not available at the moment. If there can be a demand be created, maybe it could be available in the future, but it's not available now. This was different for chitosan. In Dhaka, we did a market demand study or demand supply study of these shrimp shells, and there's enough shrimp shells available which are not used at the moment where chitosan could be processed out. So if owners would say, okay, we're now using chitosan in our treatment processes, there could be a local company could coming up and process this waste stream into a conditioner. Different points I also want to make here is that quicklime and Moringa oleifera increase the sludge mass. So, I mean, you don't want to at the end treat more sludge than necessary, that increase your costs. For Moringa oleifera, you could argue, okay, you're adding an organic material, so you increase maybe the properties of your treatment end product if you use it in agriculture. But that's usually not the case for lime, which increases the ash content, and might be useful for some soils, but not for every. So it also has implications for resource recovery. Looking at comparing all the conditions we assessed, I would recommend you looking into Kitusan. So for some of you these results are interesting, I would also like to talk to you. This is a case study just also to talk about costs. Obviously, condition is also going to cost money, and that's just from the back of the envelope assessment of Camry Faecal Sludge treatment plant, which is one of the treatment plants in Dakar. At the top, at the top of the table, you see what would be the demand of conditioners, and as you can see here, what I mentioned before, you would need around 10 kilograms per day of Kitusan, versus more than 1.5 tons for Moringa oleifera. And you can see that commercial conditioners you would actually need bigger quantities. In terms of costs, the lowest you could get would be 20% increase in operational costs. So it's significantly, but I think these numbers should be taken with care, as we don't really know so much. That's also what we heard yesterday and today. We don't know so much about real treatment costs of Faecal Sludge treatment plants. I would like to thank our partners in Dakar for supporting the study, and especially students, because these were the guys really making the research in Dakar. Thank you for your attention.
We have just 15 minutes to complete the session. We have to be very accurate and very precise.
I was wondering, does this have any impact on land requirements for treatment? Will it reduce the area required for treating the plant, and if so, how much? Any estimate?
I mean, I was saying for the case of Dakar, depending on the loading rate, the time it needs to dewater your sludge, so that all free water is percolated, is between 2 and 9 days. So if you say 50%, you will, then you end up at reducing this time by 50%. And then you have to calculate, you have to see how much area it needs, but we didn't calculate that. I mean, what you can directly say that you can increase your treatment capacity by 50%. Because your sludge goes faster through the system, and you can load more sludge on your bed.
Another question?
My name is Hanoi. I'm from Senegal. Just want to one question for the second presentation. It means you have used two different kind of plant, Fragmites, and the other plants they not have the I want to know if there are the difference between the two kind of plant related to the treatment performance.
Okay, we used two different plants. The first one was Phragmites, because this is the species recommended all over the world, and we found one local species. And the second one I mentioned, it was a local species developed by the local university of agriculture. In terms of performance, we didn't find very big difference. We can say they are comparable. But what we found, because we also measured the biomass production, I mean, which of these plants produce more biomass, and we identified that Phragmites it produced almost 2 times than the other species.
Mike Smith from Faecal, Loughborough, UK. Thank you for your presentation. Just a quick question for Maurice. When you were testing the effectiveness of the conditioners, why did you choose to use the specific resistance to filtration method? I find that a very complicated method, and I tend to use the capillary suction time method.
CST. We simply didn't have this device. Like, but why would you? What's the advantage of CST? I mean, the advantage of CST that you have a machine and it gives you a number.
It's quick and it doesn't rely on filtration, and you said you're looking for dewatering by gravity, and CST tends to use gravity.
I mean, I also found that in the literature, what was used most was specific resistance to filtration.
Hideo Harada from Sunday Fever. I have a question to Maurice. I guess the Kito-san will work like a kind of polymer as a flocculant. Did you consider any pre-treatment of the coagulant, like firstly to reduce the potential to become a more neutral situation, then try to breach the particles? So did you think such kind of combination of coagulant?
But I mean, conditioners doing, depending on how they work, they're doing both of it. They overcome surface charges and they bridge. So, which kind of treatment are you talking about?
Yeah, typically we use both for coagulant and flocculant. I don't know much about Kito-san, but I guess that is mostly work as a flocculant. So what do you think about coagulant?
With the commercial products, you can really control how they work. If it's a conditioner, if it's a flocculant, these natural ones are somewhere in between. So they're conditioner, they're flocculant, they're doing both. I mean, it also depends on where you get your shrimps from, how far you process it. If you would produce it locally, you would maybe not produce it to a degree, like a fine grade. I think it's difficult to control which mechanisms really dominant.
Both function. Yeah, understand. Thank you.
This is for Moritz question. Did you have a process for selecting the synthetic polymers before you started the testing for comparison? Because that's really important. There's a whole range of products, and in terms of the quantities that you add, there was some comparison with Kito-san, but if you have the right polymer, what you add might be much lower, and which results in a much higher cake solids. Another quick point I wanted to make is when you choose different conditioners, it's also very important to look at not just the dewaterability or the final cake solids, but how much sludge you produce in total. And you had it in your slide, but what you had was how much conditioner you add. In addition to that, there's also generation of chemical sludge. So you can add something and that can result in chain reactions and that can produce much more sludge in terms of mass compared to what you add as a conditioner. Finally, one advantage of synthetic polymers, and maybe this is something that you can look at later, but they work very well in a wide pH range or different sludge characteristics, and the organic conditioners or the biological ones, that's where they can suffer. Just some points.
Yeah, no, thanks. Excellent question. And you can see that one can see that you're an expert. Because no, you're right. The selection of the commercial products is very difficult. If you call up one of these companies, they ask you, so what sludge do you have? Is it industrial? Is it a mixture of what industries we have in your catchment? Is it simply domestic? And they talk about wastewater sludge. And I simply couldn't tell them a lot about sludge, the sludge I have. I could tell them it's septic tank sludge from Dakar. And if you call up a French company or a Swiss company in this case, they can't really tell you what product you should use, because conditioners are commonly used in wastewater treatment. So I would say it was fairly random how we picked these conditioners, and yes, they're not the right conditioners for fecal sludge. They are conditioners which are commonly used for mechanical dewatering. So they increase, like they produce really high flocks, so they're more resistant to decanting and centrifugation and these kind of things. So you're right. It could be that with other commercial conditioners, the required dosage for commercial products is much lower. pH, I would say it's not so much an issue for us because fecal sludge usually has a pH which is in the range that it's not an issue. I mean, that's usually around 7, 6.5, 7, 7.5. But because you don't have any huge influence of industries or something, it's not so much an issue. And there was a third question, which I didn't remember. What was the third point? Quantity of sludge. I mean, all the conditioners we tested don't produce a chemical sludge, which is difficult to dispose.
Lime does.
Because of the high pH.
Right.
Yeah. So that's why I'm saying that. First of all, lime. I wouldn't recommend lime because it adds a lot of ash. It adds a lot of inorganic material. But it depends on what you're going to do with your sludge. If you have acid soils and you want to use it in agriculture or as a soil amendment, it just depends what your end uses. But I agree. Like lime would be the one I would definitely recommend.
Yes. The last question from the moderator to Maurice. What about the botanical from if we realize we use moringa, it enhance the quantity of organic matter you have in the area. If you want to detect the relation, you realize how difficult it will be in the community science.
Yeah, so that was not the focus of our research, but we kind of looked at it, and there's was a study before that with moringa at dosages where you can have an impact on dewatering, your effluent in terms of nutrients and COD, BOD is increasing. So you maybe have better dewatering properties, but at the end you have more treatment of the effluent.
Okay, a big clap for this.